All right. Hello, everyone. I'm Giorgos Argyriou, and I'm a fellow of the RACE project in the University of Cyprus. Today, I'm going to present you my research area, my progress so far, and how multivariate data analysis can help us for following data that are produced on the edge of the network by IoT or edge devices. Okay. Like all fellows of the RACE project, I'm a PhD student. I'm a member of the Laboratory of Internet Computing in the Department of Computer Science in the University of Cyprus, and my supervisors are Professors Marios Dikiakos and George Palis. I am the Early Stage Researcher 1, and the title of my subject is Adaptive Monitoring Framework for Wearable Devices. According to the RACE project architecture, my topic is here in this orange frame. Wearable devices, which are essential for the Internet of Sports, are usually characterized as Internet of Things or IoT devices, and are part of the cloud, fog, edge, and IoT environment, which is depicted here in this picture. The cloud is the upper layer in this figure and has been widely used since almost 2005. When we think about the cloud, we consider that it almost has unlimited processing power and unlimited storage. Cloud consists of thousands of devices, and we are never concerned about power consumption. On the other end, in the lowest layer, IoT devices were introduced since 1999 for supply chain management, but later adopted by healthcare, home, environment, and transport. The last 5 years, IoT devices are increasing in numbers, and soon they will be everywhere. IoT devices are already in billions. The layer in the middle, we call it fog or edge. This layer involves base stations, routers, even smartphones, and many other devices. Raised by the fact that I'm usually asked how we categorize devices in edge and fog computing, I will elaborate more on that issue by presenting how these layers are described in publications, how they are realized, and some other representative use cases. Starting with the IoT devices, as I said, they were introduced in 1999, but the last 5 years are increasing in numbers, and soon they will be everywhere. In 2008, the US National Intelligence Council presented 6 technologies with potential impacts in the US. One of these technologies was IoT, and their point of view was on IoT was the following. Internet of Things is the general idea of things, especially everyday objects that are readable, recognizable, locatable, addressable, and controllable via the internet, whether via RFID, wireless LAN, wide area network, or other means. Later, in 2012, in the Singularity Summit in San Francisco, it was estimated that already 5% of human-constructed objects had embedded microprocessors. So what's usually an IoT? Okay, with the history, but what do we think about an IoT, how an IoT looks like? It consists of at least one sensor, a microcontroller, but nowadays a microprocessor, usually of ARM architecture, and an energy source. What an IoT is going to monitor and where is going to be placed define the size, the shape, and most important, which is the energy source. So right now we have several categories of IoT devices. We have wearables, IoTs on clothes, on electrical appliances, on cars and buses, and buildings, or on buildings, and many more. So that's all about IoT devices, which are on the one end of the environment, with cloud being on the other end. But what is going on in the middle? In the middle of the environment, we have fog and edge. And now things start becoming blurry, or I can say foggy. If on the one end is the cloud, which is realized with data centers, and on the other end, we have an activity tracker equipped with, for instance, a heart rate sensor or an accelerometer, what's going on with routers, smartphones, cloudlets, gateways? This question is answered with probably the most famous scientific answer, which is, it depends. Okay, it depends, but on what? So from what I studied, it depends on the researcher that does research and publishes a paper and the use case that it is approached. So let's see some use cases and focus on terminology. The first is from the Edge IoT, mobile edge computing for the Internet of Things, where they propose to equip base stations that are used for mobile communications with computing nodes, which are called fog nodes that provide virtual resources to users, as you can see here in the red circles. So in this use case, we have people moving around in the city with IoT devices on their cars, on their bodies, and the fog resources are virtual machines living in computing nodes that are installed next to base stations, which initial goal is to provide mobile telephony. This proximity to the user gives the advantage of providing low latency services. On the other hand, we have Fogify, a fog computing emulation framework. Fogify is an emulator that eases the modeling, deployment, and large-scale experimentation of fog and edge testbeds. Even though I really like it as a tool, and I believe it can be very helpful for most fellows here and most researchers that are willing to create evaluation testbeds, I will focus again on terminology. Here in this paper, every device that has the ability to do computation is considered to be a fog node. So if we ask the researchers in these two use cases, how do you categorize a smartphone or a Raspberry Pi equipped with sensors, you'll get two different answers. The first will say that a smartphone is an edge device that holds sensors, so it is on the IoT layer, while the second will say that it's a fog node. On the other hand, if they are asked about an access point with a gateway, they will agree both that such resources belong to the fog layer. So who is right and who is wrong? The answer is no one. Each team of authors described accurately what they consider IoT, edge, and fog, and they are all right. Now let's see how I define all these layers and how I categorize all these devices. On the one end, we have the cloud, of course. On the other end, we have the IoT devices. In this image, I only depict wearables because when I'm thinking about use cases, I'm thinking Internet of Sports, and wearables are the most usual device with sensors. Now, let's see here how we can have edge and fog devices, which I categorize in two different layers. In the edge layer, battery-powered devices are included. So we have smartphones and enhanced routers. In the fog layer, we have computing resources that look like small data centers. They are usually called cloudlets, and they are close to the user. The problem with the devices that I mark with orange here in the slide is that they usually exist in research. They are not apparent, and especially the fog layer has not been fully realized yet. But okay, why I'm saying all this is because we have to understand what kind of resources we have, how they can be organized, and what requirements they put. And that way, we can define the real problems and propose efficient solutions. So let's see some basic characteristics of the edge and the fog layers as I describe them. In the fog layer, we have resources that look more like a tiny data center, and usually such resources are Raspberry Pis or other types of small computers. Or as we saw in the edge IoT case, maybe they can be virtual machines that are deployed on computing nodes that are close to base stations. Such resources have fixed positions. They have relatively large bandwidth because they are connected either with Ethernet cables or Wi-Fi, and they are plugged, so we do not really care about power consumption. One of the main challenges is how to organize such infrastructure. A widely proposed solution is the serverless programming model, for which I did some research last year. In the edge layer now, we have standalone resources, which are usually personal, so think something like a smartphone. Here, the edge resources are mobile. The connectivity is intermittent and costs either in money, because we usually pay more for mobile data, or in battery consumption, because when we use mobile data, the battery drains faster. And also, they are battery powered. The biggest concern here is how to lower the power consumption. Several ways are already proposed, focusing on lowering data dissemination, and there's more to search in this direction. The use case I'm working is influenced by the Internet of Sports. In the IoT layer, we have battery-powered devices that are usually wearables. In the edge layer, we have smartphones, and also we have the cloud as always. The data flow in this use case is the following. We have data that are produced by the sensors on the wearables. They are disseminated to smartphones, usually through Bluetooth. They are processed and useful information is extracted there. And eventually they reach the cloud where they are stored for further processing, or they stay there for long-term storage. This kind of logic is being followed by several companies. If you think about it, whoever in the audience owns a Xiaomi band, a Fitbit, or some other more or less famous activity tracker follows this exact pattern I just described. Now, my focus is on lowering power consumption of IoT devices. These devices have low capabilities, so they request to be paired to a stronger device, usually a smartphone, with which they usually communicate through Bluetooth. They gather data continuously, and whenever they connect to the stronger device, they unload the data and therefore become lightweight again to continue monitoring. It is estimated that 30% of all IoT devices are using Bluetooth Low Energy as the enabling communication protocol. So there's no wonder why wearables like activity trackers fall into this category. Such products conduct three main activities: computation, sensing, and data transmission. Power consumption analysis of Bluetooth Low Energy commercial products has shown that data transmission is the most consuming activity. And also, transmitting data over Bluetooth costs tens of milliwatts, while computing at full power costs only tens of microwatts. Based on all these facts, I argue that data dissemination will improve energy sufficiency of battery-powered IoT devices. Thus, I search for a data reduction technique in order to lower the amount of data transmission. And generally, as the numbers show, it's better to do computation than doing data dissemination. It's less expensive in terms of power. Now, there are already several proposed solutions that reduce IoT data by focusing on the produced univariate metric streams. So what is a univariate metric stream? Univariate metric streams are being produced by sensors that monitor scalar physical quantities. In such a case, every time a sensor is activated by the IoT device, a sample that consists of a timestamp and a value is created. For instance, think of a heart rate sensor. But the wearables that are used in the Internet of Sports usually have more than one sensor. Most of them have a heart rate sensor, an accelerometer, and a gyrometer. You can find even more sensors like the ones I refer here, like GPS, thermometer, but the top three are the most used ones. The first, the heart rate sensor, monitors a scalar physical quantity and thus produces a univariate metric stream. The other two monitor vector physical quantities, and as such, they produce multivariate metric streams. Considering the IoT as one entity, because all its sensors monitor the same body with the same focus. For instance, we put once an IoT on the chest of someone, on the foot or on the hand, so they're focused on a specific point in a specific body. We can think that all the produced metric streams as a multivariate one. The number of the dimensions of this one multivariate metric stream depends on the number and the type of the sensors. So it's different every time in every use case. For instance, the IoT device that is used by RaceFox has an accelerometer and a heart rate sensor. So dimensionality here, as you can understand, it's 4. What I'm researching currently is whether I can exploit correlations of different dimensions in a multivariate metric stream and lower the amount of data that need to be sent from the IoT to the upper layers with a focus on reducing power consumption on IoT devices. The requirements of the system model are going to define the solution format. For instance, if I focus on IoT devices that have storage capabilities, the requirements are pointing to a solution that involves compression. In this case, every time sensing is triggered, data are produced on IoT and can be stored on IoT. So if there is a time window when the IoT is not sending any data to upper layers, then there is room for compression to happen. There are already several proposed solutions pointing into this direction, and I will show you one later. On the other hand, there is the key factor of timing. If I try to address a system model where the IoT device does sensing and almost instantly data dissemination to the upper layers happen, then there is no time window for compression, and the requirements point to solutions that act immediately or in place, as we say. And of course, I will present you some proposed solutions again later. The last key requirement of the system model is the most general one, and it is the capabilities of the IoT and generally of whatever device. If I find an efficient solution, but such a solution cannot fit into the IoT device because of low capabilities, then I need to adapt it and split such a solution and have part of it running in the IoT device and the other part on an edge device. Or if we have, for instance, a different use case with a fog layer, then we split the solution. I will try to split the solution between IoT devices and the fog layer. In any case, where I'm aiming is to a solution that lowers power consumption of IoT devices and a solution that guarantees a certain level of accuracy of the reduced data, comparing it with the original data. And these two, the last is about evaluation. The way we are deciding to do evaluation also depends, and we will see it later. Now, give me some seconds. Now, from this point on, I will present you some proposed solutions that focus on lowering energy consumption in IoT devices. What I'd like you to see is how the solution format changes when we change the requirements even slightly. The first paper has the title, Sprints, Time Series Compression for the Internet of Things. Sprints is a time series compression algorithm that achieves state-of-the-art compression ratios with minimum memory and adding virtually no latency. In this setup, the key challenge was to reduce the size of the transmitted data without sacrificing its quality, because lower quality reduces data's utility. So it's lossless. What the researchers want in this case is to compress data at the sensing devices, meaning on IoT, but existing compression algorithms violate the memory and latency constraints or perform poorly on sensor-generated time series. Their solution, on the other hand, manages to do compression with having a small block size, so the solution can fit into small memory and also not to increase latency. Also, it performs with a high decompression speed, so the server that gets the data can decompress and use them quickly. And this algorithm is also lossless and preserves all data. In terms of performance, the Sprints algorithm needs almost less than 1 kilobyte of memory to work, and the decompression can be done in more than 3 gigabytes per second rate in a single thread. A key component of Sprints' operation is a novel vectorized forecasting algorithm for integers. It exploits temporal correlations in each variable's value and variance, and has the potential for parallelization across different variables. Also, this forecasting algorithm can train online, but it has a serious limitation, which is that it can be used only for integers. Another solution based again in compression is an energy-efficient approach for IoT data collection and analysis, which was proposed in the paper, an energy-efficient IoT data compression approach for edge machine learning in 2019. In this case, the researchers propose a fast error-bounded lossy compressor prior to transmission. The data are again rebuilt or decompressed, as we say, in the edge node, or generally in an upper layer after they are produced in the IoT device. Eventually, in the use case that is described, these data are being used for supervised machine learning. It's the next step. So why is this important? I'll explain to you in a while, because it has to do with the evaluation that happens in this work. The SZ, as they call it, compression technique, manages to compress multivariate time series that contain diverse features with different scales. And it is indeed lossy compression, but it controls that level of error by employing an error-bound technique. In this use case, in the use case that is being communicated, let's say, in this paper, we have data of vital signs that are collected by IoT devices, which are attached to a driver. These devices send the data to the upper layer and practically to a server where the driver's behavior is being monitored. So it's an intelligent vehicle system, as they say. As for the evaluation of this compression algorithm, it is fully based on the use case. The data, they say, okay, that the data are reduced by up to 103 times, but the researchers focus only on the quality of the medical data and basically of the information they were going to extract. And according to it, the driver's stress level detection was not affected. So basically what they're saying is we have an algorithm that reduces data. It is a lossy compression, so we will lose some data, but we were going to use this data for supervised machine learning. So we check if these algorithms, how these algorithms perform with all the data. And if these algorithms perform the same with less data, so our compression, even if it's lossy, it's okay, because we get the same results in the end. Now, let's leave compression algorithms, which is one basic, one category, and go to other techniques for dealing with time series data. Again, on Univariate. ADAM is a framework developed in the lab I'm working and was published in 2005. You can see the citation at the bottom of this slide. It is a lightweight adaptive monitoring framework for smart battery-powered devices with limited capabilities. What it does is adapting the monitoring intensity in place by using adaptive sampling and adaptive filtering. Every time a new sample is produced, the value is processed and one step ahead estimation is provided. That way, a new sampling rate is proposed after each sample. The filter range also changes and its width adapts according to the metric stream evolution. ADAM is able to identify abrupt transient changes and it runs on the source device. I worked with ADAM a lot. I translated from Java to Python and did several experiments using data provided by RaceFox, and part of them I will present later. Admin now is another framework that was developed in the lab I'm working in, and the paper was published in 2017. The title is Admin, Adaptive Monitoring Dissemination for the Internet of Things. Admin is a low-cost IoT framework that reduces on-device energy consumption and the volume of data disseminated across the network. Admin adapts the rate of dissemination by acquiring knowledge at runtime. This knowledge involves stream evolution, variability of the stream, and seasonal behavior of the stream. In contrast with ADAM, it sends an update of the estimation model instead of the real stream. It takes into account the seasonality of the metric stream, but also checks with statistical tests the efficiency of it. As in ADAM, it also runs on the source device, but the receiver must be tuned to receive also the model instead of only the data. Now let's go to the difference and understand in more depth what these algorithms are doing. ADAM receives the samples from a source one by one, and each time calculates the importance of the sample and defines the sampling period. When samples are filtered, the last sample that is sent is taken into account. On the other hand, in admin, admin works in cycles. It uses a small and specific amount of data for training, then creates an estimation model and sends the model instead of the data. The receiver continues to produce the data according to the model. Even though admin filters the data and do not disseminate, it continues receiving them from the source and evaluating them. the moment it realizes that an unexpected sample is produced and a sudden change happens, it stops the cycle, sends the unexpected sample, and a new cycle of training and model creation starts. These characteristics make Adam more suitable for data that are going to be processed, while admin is more suitable for data that are going to be disseminated. Before going to Adam's performance, as I told you that I did lots of work with it, it's good to explain how Adam is evaluated, what was selected for evaluation. First of all, it has two user-defined parameters that the user can change them and check its performance. One is Tmax, which is the upper limit of the sampling period, and the other is called G, which is the acceptable imprecision of a reconstructed metric stream. More specifically, we can see that after we calculate the level of confidence, G is playing here in this equation. We can see that G is playing a major role on the sampling period that is going to be defined. So, and also it works like a threshold. Now, what is Adam's performance? Every time we run a data set through Adam, it does adaptive sampling. Eventually, the output is a compressed time series, but okay, it's not the usual compression that happens. Okay, it's not that we have the whole data and then we do compression like it usually happens when we have compression algorithms, but the final results looks like a compressed time series that has less samples or less data than the original. So we treat it equivalently. The amount of the sums that are outputted divided by the amount of original samples is the compression. So pretty easy. The level of accuracy now is defined by the error. Basically, it's the opposite of error. The less the error, the higher the accuracy. Generally, we want high compression with the lowest possible error. The conclusions from the preliminary experiments show that Adam's performance and tuning for datasets for the same KPI is similar, and the tuning for parameters for best performance is more or less the same. Of course, there were datasets that Adam had a very, very good performance, and datasets that where it performed very high compression while the error was very low. But okay, of course, there were some datasets that error was a bit worse. So I will show you two of them. I did many more with the datasets I had, but I want to be short. Here, with heart rate, with data from heart rate sensor, Adam had the best performance. Through all 10 heart rate datasets I ran, Adam achieved compression levels around 80%. So it's in the end, the IoT device that is going to use Adam can send only 20% of the data. And the error was amazingly low at 0.15%. And here in this chart, you can see the red is what Adam would send, and the blue is what initially what the initial data were going to be sent. Also, you see only 1,000 samples, a part of this 6,631 sample data set, in order to be able to see the details. So as you see, we can. It's very, very efficient, but it works on univariate metric streams. In other data sets, like the symmetrical, here Adam's performance is a bit worse than before, but the overall performance is pretty good. And we had generally we had very positive reactions from RaceFox. In SYMM data sets, Adam achieved compression levels at around 70%, with error being around 3.5%. Again, the data set is pretty large, so I show you just a part of it. where again the blue line is the original time series, while the red is Adam's output. As you can see, we have techniques for univariate metric streams with univariate data metric with univariate data analysis. We have compression techniques either for univariate or for multivariate. But what we do not have right now is doing multivariate data analysis and try to approach this problem from this point of view. Up to now, I haven't found any solution being proposed, and this is the way I'm going to see all the data as one big multivariate metric stream, and try to find correlations in order to eventually reduce data dissemination and improve and lower power consumption in IoT devices and in edge, in battery-powered devices in general. So that's for me. Thank you very much. And if you have any questions, I'm pretty happy to answer.
Thank you. Thank you very much for the very interesting presentation. So maybe I will start with one question.
Okay.
When you discussed about these other techniques that are basically lossy compression that still does not affect the final quality of the downstream processing tasks. Those were machine learning tasks, the one that were using downstream.
You are talking about sprints or the next? Because
if you can go back, I will tell you if it's
sprints is lossless. Sorry. Also, so, Adam and admin are lossy too.
Yeah. No, I was thinking the one before, the one. Yeah, this one that you said. So they were using in the end. Yeah, for machine learning. Okay, and my question is, did they choose how much to compress based on trial and error? Or did they have some automatic way to deduct from the machine learning system how much compression would be good? So, or did they have to manually find out how?
What they say is that the compression technique, first of all, they took this compression technique and adapted it to be able to run in IoT devices. So they had to kind of lower the way it works in order to fit. Second, what they say is that it's lossy, but we can calculate the error because we lose data. The error comparing this data with the initial data. So we can have a boundary in order not to compress, not to lose many data and have a very big error. Now, as for the supervised machine learning, it is that they are talking about in this paper. It's just a procedure. It's just a different procedure. It's a procedure that happens later in their use case. They say that these data were going to be used for some supervised machine learning algorithms. So we are going to check our efficiency based on if these algorithms are continue to work the same. So it's a successful compression. I don't know if I covered you.
Okay, yeah, I think you answered. So because what I was thinking when you were presenting this slide is that when you have multivariate streams, supervised machine learning might be more sensitive to a certain dimension rather than another. So, so what you might want to have is that you might want to have a system that can be more aggressive in compressing certain values rather than others, because the downstream task is less sensitive to those. So there is more that you can exploit there in terms of you can afford a bigger error in some dimensions because the ML system does not care about those or doesn't care that much. So that could be something that could be interesting to explore in certain scenarios.
This is what I'm going to do, at least with one of my secondments, basically. First, right now I'm searching about how to do multivariate data analysis, how to benefit from this fact, having some requirements for my solution, that my solution, okay, should be like this and that. But I'm going to collaborate with Deba, and he's doing machine learning. So what we're going to do, basically, for the collaboration, what I was thinking is not to change a lot direction, each one to stay in his path, but also to deviate a bit in order to meet one another. So, for instance, for my deviation would be, okay, let's say I have a sampling technique that lowers the data, but what happens later? And Deba is going to be to this later thing. So I think I will have, and Deba will have opportunity by such a collaboration to see the things as you described.
That looks very, very interesting. So yeah, good luck. I think it's a very, very interesting topic that you're gonna go on. So yeah, thank you very much. Do you have other questions, guys?
Yeah, I have one question about your approach, Adam. Like you mentioned that it is not applied to, that basically it is again lossy compression, but it is like not applied to the whole data. So like my question is, like, I don't know if I understood it correctly. Is it applied independently to each sample of the data, or like is it does it like a downsampling or what?
Yes, exactly. I will explain right away. What Adam does is, first of all, it doesn't see the whole metric stream, and secondly, it sees only sample by sample. So a sample comes to it, and it calculates some metrics, which are like average, but it's not the usual average we know. It's another kind of average. Based on exponential weighted probability. So, but let's not be that technical. So every time a sample comes, it takes the value of that sample. It calculates, let's say, some metrics, some analytics, and keeps only these analytics, which are basically 4 or 5 numbers, 5 float numbers or something like this. And also keeps this sample, the value of this sample. When the next sample comes, it reevaluates these 4 or 5 analytics and tosses the old sample, and it doesn't keep any history of the metric stream, and does work only with the new sample. So every time a new sample comes, it knows only the previous and the new that comes, and some analytics which are 4 or 5 float numbers, and that's all. So every time it calculates, based on these analytics, it calculates a new sampling period. For instance, if you have a heart rate sensor, usually heart rate sensors by design, basically the IoT devices by design, say, okay, I will activate the heart rate sensor every 1 second, and I have every 1 second value. Now, Adam comes here and says, okay, put me in the middle. I will get its sample, I will get its value. I will evaluate how important this is. I will keep metrics about how the stream, the whole, all the value, generally how the stream behaves. And every time, in every sampling, every time that I have a new sample, I will tell you how important it is in order to send it or not. So it tells you, okay, I will define the sampling period. Okay, you say and you design that it is 1 Hertz, so every second. I will tell you, no, later, for instance, that you need to, you have to have a bigger sampling period, so less samples. Or I will tell you according to how important the sample is or how much the change is. I will tell you, okay, to be 1 second. And this is done after every sample.
Okay, I see. So, okay, I get it. It's basically, so it's basically adaptive. Like when, like you see that you have a sort of data stream which isn't changing much. You leave, you can leave like allow a larger period. Instead, when it has abrupt changes, it needs like to update more often. That's more or less the idea.
Yes, yes, exactly. And it tells you, okay, if we cannot, then we go to the system level and we say, okay, the first usage is, okay, put it in the middle and you will send less data to the receiver, okay? But, okay, if the IoT device has, if you can really define the sensing, the sampling, the sensing that the IoT device has for a specific sensor, we can also not sense at all. So you gain both by not sending the data and not sensing. Sometimes sensing is also power consuming. But the first focus was on dissemination. And this is about the question that Stefanos did 2 days ago about we have Fitbit, we can say, we can define a different sampling period. Can you do something about that? Yes, basically we can, even with a sampling period. Sensing,
okay, thank you very much. You were very clear. Also, can I ask you, like this heart rate data set that you used for your experiments, like is it provided by RaceFox or like is it from somewhere else, from some other sources?
No, it was provided by RaceFox specifically. Okay. We talked with them, we showed these algorithms and our focus in the near future. And they gave us some data to see how these algorithms perform. And now we are going to the next step.
Okay, good, thank you.
So maybe no one else?
I think if no one has any more questions, then I think we can again say thank you to Giorgos for his very nice presentation.
Thank you very much.
Thank you everyone for attending. And yeah, I guess see you next year with the new seminar series that Giorgos will take care of organizing.
Nice.